In this video, I'm going to be discussing cycloalkanes. And so in the previous video, I was talking about alkanes, or what are sometimes called N-alkanes, which are linear alkanes. So that would be something that looked like this. So this would be a hexane. And so now we are going to look at cycloalkanes, which are molecules that have a ring closure. And so it would be sort of taking this carbon here and bonding it to that carbon there. And so this is going to introduce some new chemical and physical properties to our molecules here. And so the first two we're looking at here, so this is cyclopropane and cyclobutane. So remember, propane is a 3-carbon hydrocarbon and butane is a 4-carbon hydrocarbon. And so I have the hydrogens put explicitly here, and then this is just the line drawing. And so the line drawings are the ones that we're going to have to get used to seeing. And so this is probably one of the last times I'm going to be sort of showing the explicit hydrogens here on these. And so just know that when you see just kind of a triangle sitting there, that is a cyclopropane, and then a square is a cyclobutane. Then we have cyclopentane. So with cyclopentane and cyclohexane, I'm going to give a little bit more detail here, just because the 5-member and the 6-member rings are the ones that we're going to be running into routinely throughout this organic chemistry. And so those are kind of the most important. As we'll see here in a little bit, these two right here, like the cyclopropane and the cyclobutane, have some what's called ring strain. So these are actually not that stable of molecules, where the cyclopentane and cyclohexane are quite a bit more stable. And like I said, in this organic chemistry, and if you go on to biochemistry, you run into the 5 and 6-member rings probably most often when we are talking about ring structures. And so it's those two, the 5 and 6-member rings, that I'm going to be talking about sort of the most here. But if we want to look at some physical properties here, so we have the cyclopropane to cyclooctane. So we have the boiling point for them and the melting point. So melting point going from solid to liquid, boiling point going from liquid to gas. And so to put this in context, I've graphed the melting and boiling point of the cycloalkane. So in blue here is the cycloalkane melting point, and in orange is the cycloalkane boiling point. Then in gray right here is our linear chain melting point, and then in this sort of yellow here is our linear chain boiling point. And so what you'll notice is that the melting point of the cycloalkanes is a little bit higher than for the linear, and for the melting point here, we have actually a little bit even higher. Or no, so these are the boiling points, and these are the melting points here. And so we see that for the cycloalkanes, they're both a little bit higher compared to the linear alkanes. So the reason for that is because with the linear alkanes, remember, we have well, in alkanes in general, we have this freedom to rotate around these single bonds, these sigma bonds. And so I've shown a few different sort of conformations for hexane right here. So we could have that, and then if we rotate around that bond there, we get something that looks like this. If instead we rotate it around that bond there, we get something like this. And if we're rotating sort of one way or the other around that bond, we can get these two things here. And so this sort of degree of freedom makes it so the stacking of these is a little bit less I guess, efficient, and so you don't get the van der Waals forces. I mean, you're going to get good van der Waals forces, but it's going to inhibit those van der Waals forces by a little bit, which is why we see only kind of a slight increase in the melting and boiling points of these cycloalkanes here. And so the reason for that is because if we have a cycloalkane that looks like this, then the freedom to rotate around these bonds is constrained by the fact that it has to stay bound to these other two carbons on either side. And so we will see here in a few minutes that there is some sort of conformational changes here, but it's not as free to change conformations as the linear alkanes are. Before we get into that kind of stuff, we once again have to get a little bit of nomenclature out of the way. And so if we, as we saw before, if we just have the non-substituted, then we just call it cyclopentane. But for here, if we put some substituents on, so we have now a methyl group on here, so this is methyl cyclopentane. So then we can have 1,1-dimethyl cyclopentane. So we have these on here, and so this is the most substituted, so this carbon will be our 1 carbon, and so we call this 1,1, and then we want to number it going around this way towards the next closest substituent. So that's 1,1,3-trimethyl cyclopentane. We can have, say, 1,1,3,3 tetramethyl cyclopentane, so tetra here meaning 4. So that is sort of the way that the naming is done there. Then we can also have, so this is now on hexane, so we have this tert-butyl group here, and so we will just call that tert-butyl cyclohexane. So then when we put a sort of more complicated substituent on here, we then have to sort of name that substituent in addition to the cyclohexane. And so we will actually put that in parentheses here. So 1, 2, so this is the 1 carbon on our substituent and our 2 carbon on the substituent. And we have a methyl group here and a methyl group there. So we call it 1,2-dimethyl propyl. So this is propyl since it has 1, 2, 3 carbons, so 1,2-dimethyl propyl, and we put that all in parentheses, and then we put cyclohexane because this is a substituent coming off of our cyclohexane there. And so now we also have these cis and trans bonds going on here with our cyclic alkanes here. And so what we have shown here, and I have this shown kind of 2 different ways. So this is sort of a projection where this thicker part is supposed to be sort of coming out of the screen a little bit, and then this thinner part is sort of going, sort of sticking in the screen a little bit. And so we have trans where we have one sort of coming down and one going up, where if we want to sort of look at it from the top, we can think about it this way, where this wedge is sort of coming out of the screen, and then this dotted wedge here is sort of going into the screen. And so we call this, because they are sort of sticking up and down, so in different directions, we call it trans. Then this is the ethyl group, this is the methyl group, and so it's trans 1-ethyl. We count this as the 1 carbon because it has the higher priority, the sort of larger substituent on it. So 1-ethyl 2-methyl, or trans 1-ethyl 2-methyl cyclohexane. Where if instead we have this methyl group coming out in the same direction as this ethyl group, then we call it cis. So this would be cis 1-ethyl 2-methyl cyclohexane, where this is just sort of looking at it from the top rather than trying to have it sort of stick in and out of the screen. And and this is something that we already sort of saw in the previous video. A big part of organic chemistry, especially this 200 level, this sort of sophomore level organic chemistry, we start just introducing a bunch of these different ways of trying to draw these molecules. And so not just the study of the molecules themselves, but of ways to actually show the molecule to try and show 3D structures. So like in the previous video, we introduced like Newman projections. And so just kind of a note on that here is just that a big part, like I said, of this 200 level organic chemistry is just introducing ways of portraying molecules. And so, yeah, that's just kind of something to keep in the back of your mind, is that that's something that we will see more of going forward. In fact, here we are now getting to, so this is another Newman projection. And so this is what I was talking about with the ring strain. So this is the Newman projection of cyclobutane here. And so we have this going forward. So remember, the cyclobutane is sort of that square shape. So we are sort of looking at it from that direction. And so we now have this right here with this. This is the front carbon. This circle is sort of that back carbon behind it, and same on this side. And so we are looking at this. So what we see is that we have these eclipsed hydrogens on here. So that's adding some steric strain onto it, as those hydrogens will sort of interact with each other. But we also have this bond strain on it. So in a square, the bonds are going to be 90 degrees, where, remember, with these sp3 carbons, they want to be at 109.5 degrees, and so we have this loss of 19.5 degrees, and so we actually have some bond strain on it, where the bonds want to be at this 90 plus this 19.5 degrees, but because we are in a square, we are being sort of constrained to this 90 degrees, and so that creates some strain on the bonds from the carbons here. And same with the cyclopropane, but now the bond strain is even worse because we are constrained to these 60-degree angles. So we are losing 49.5 degrees on what these bonds want to be. And so this up here is just showing with these hybrid orbitals here. So the hybrid orbitals in sigma bonds, which is what we have in cyclopropane, like to be sort of N-on. So they like being sort of like this, where what we see in the cyclopropane, they are now at this angle here, instead of being nice and sort of linear and straight on with each other. And so that is creating some strain on there, which is why the cyclopropane and the cyclobutane are sort of unstable ring structures. And so this is cyclobutane. So what we do see with cyclobutane to try and relieve some of that strain is that we get these this sort of puckering going on here, where in 3 dimensions we get that the that sort of, this carbon and this carbon will sort of stick out of the screen, while this one and this one sort of stick into the screen. And of course, there is an equilibrium where it is sort of oscillating between the way that it's folded a little bit like this. And so with the cyclobutane, at least, we can get a little bit of relief on this angle strain here by having a little bit of puckering going on, where that tends to be not possible with the cyclopropane, just because we have just a triangular shape. All right, and so now we can look at like a Newman projection here. So this is actually cyclopentane. So I'm going to go down here just so we don't have that name up there. So this is actually cyclopentane. And so we again get sort of a puckering going on, sort of this sticking up. So if we look at that in a Newman projection, it looks more like this, where it sort of goes up then down and like that, where this is sort of N-on going in and out of the screen. And so we get sort of a puckering with that. And in fact, this fold going up like this is in an equilibrium where it sort of undulates around the ring. So this one will go down while this one comes back up, and then this one will go back down while this one comes up. And so that sort of fold up like that sort of moves around the ring structure of the cyclopentane. All right, so now we're going to move over here. So now we're going to look at the cyclohexane. And so remember, this is our cyclohexane, but we're going to get some conformational change on this as well. So this is a Newman projection for that. So sort of looking at it this way. So this carbon is kind of sticking out of the screen. This one's going into the screen. And then so this carbon will be eclipsed by this one, and this carbon eclipsed by this one. So we get a Newman projection that looks like this, where this carbon is sticking up, sort of like this one sticking out of the screen, this one sticking down, sort of like this one sticking into the screen. And so this is the sort of favored conformation of cyclohexane. And it can take on sort of two different conformations. So what we're looking at up here with this Newman projection, with this right here, is what is called the chair conformation, but it can also be in what's called the boat conformation. And so we have the chair conformation. It's called a chair because we have one carbon sort of sticking up and another one sort of sticking down, while these two are in the plane of each other, where the boat conformation has both of them sticking up like this. And the chair conformation is actually the more favored one. So we can see the energy diagram for this, where the boat has somewhat of well, I guess it's a local maxima within a local minima here. So the twist boat conformation, where this carbon is sort of twisted out and this one twisted in, is a little bit more stable here. I'm going to erase my drawings on here so we can see it a little bit clearer. So these twist boat conformations are a little bit more stable than the boat conformation. Then it will pass through these half chair conformations, which are energetically less favorable. But then we see these chair conformations here being the most energetically favorable. So remember, we're always trying to reduce the amount of energy as much as possible. And so these chair conformations tend to be the most energetically stable. And so if you're looking at, like a mix, well, not a mixture, but the compound, like, you have like a beaker of the compound, you're going to find that most of them, so you take a snapshot at any given moment, most of them will be in the chair conformation. So the second most will probably be in these twist boat conformations, then the third most in this boat conformation. Then these half chair conformations will probably be just sort of a transient sort of conformation that this takes. All right, so then the plot thickens a little bit when we start adding substituents onto our ring. So now we are adding this methyl group onto it. And so what we see is that these substituents like to be in what are called the equatorial positions. So these two are in chair conformation here. And so if it's in one chair conformation, we have what's called the axial group here, where here is equatorial. And so with equatorial, it's sort of sticking out from it, where axial is sort of sticking up. And what we'll see is in the axial, we have some steric interactions with these other hydrogens here, where in the equatorial there is less of this steric interaction with it. And so what we get, so if we want to look at it in the Newman projection here, we want to get the axial going on, and we want it to be anti here to this, to like this carbon right here. And so the sort of rule of thumb here is that the larger groups always want to be in the equatorial position. So one chair conformation is going to be favored over the other based on whether that larger substituent is in the equatorial or axial position. But of course, then we start getting multiple substituents on it. So here we see that we can have the cis where they are both sort of sticking in the same direction. So like the cis 1,3 dimethyl cyclohexane, or we can have the trans where they are sticking in different directions. So the trans 1,3 dimethyl cyclohexane, where we see this one is in equatorial, where this one is in axial, where with this cis we have two here in the equatorial. And so we have to look at the stability of each of these. And so these are some of these di-substituents here. So we can have it on the same carbon. So that's the 1,1 dimethyl cyclohexane. So that because it's sort of equal whether or not it is, we have one in the equatorial and one in the axial. One chair conformation is going to be interchangeable with the other, and so neither one is going to be favored because we will always end up with one in the axial, whether it's up or down, and one in the equatorial right here. But then when we get to the substituents being on different carbons, so we can have the cis 1,2 and trans 1,2. So the cis 1,2 dimethyl cyclohexane, so both ring flip isomers are identical, so we will always have one in the axial and one in the equatorial here. Where with the trans 1,2 dimethyl cyclohexane, we have one that is where both of them are in the axial and one where both are in the equatorial. And so this one here is going to be much more favored over the other. Where with the 1,3, as we saw with the cis, we can have both in the equatorial or both in the axial, and so the one with both in the equatorial is going to be much more favored. Then when we have the trans 1,3 here, we're going to always have one in the axial and one in the equatorial. And so neither one of those are going to be favored. So both forms are identical. Then when we get to the 1,4, so we have the substituent on sort of opposite ends of this cyclohexane here. So with these cis, both ring flip isomers are identical, and so neither one is going to be favored over the other. So then with the trans, this is both equatorial, this is both axial, and so this is going to be the favored conformation right here. So the order of increasing strain is predicted to be, so the trans 1,4 dimethyl cyclohexane is equal to the 1,3 dimethyl cyclohexane, or the cis 1,3 dimethyl cyclohexane. The trans 1,2 is going to have this plus 0.9 kilocalorie per mole. Then the trans 1,3 is going to be equal to the 1,1 dimethyl cyclohexane, which is going to be equal to the cis 1,4 dimethyl cyclohexane. Then the cis 1,2 dimethyl cyclohexane has this increase of 2.7 kilocalories per mole. So that is going to be, so remember that is this one here. So those ones are both equivalent there. And so, yeah, that's just a little bit of looking at having these single methyl substituents. So then if we start making one of these substituents larger, so if we make like one of them into a ethyl group, what you'll see is that so like for instance with like the 1,1 like right here, so if one of these was then a ethyl group, then what you're going to see is that the ethyl group is going to be in in the equatorial position. So the larger substituent always wants to be in the equatorial position. So if you start altering these methyl groups to make one larger than the other, just know that the larger one is always going to want to be in the equatorial position. So the more stable conformation is always going to be with the larger substituent in the equatorial position. And so that's just the rule of thumb for which conformation is going to be the most stable. All right, so switching gears, we can also have what are called bicyclic molecules. So that is like two ring structures put together. So this can be done in multiple ways. So we can have the fused bicyclic, where it looks just like this, where they just sort of share kind of an edge like this. We can have the bridged, where now we have this cyclohexane here. So we have 1, 2, 3, 4, 5, 6. But then we have this other carbon that sort of bridges this carbon right here. And this one, which is why those ones are circled in red, and those are called the bridge head carbons, because those are where the bridge connects it. We can also have what are called spirocyclic, where the two just share a single carbon in the middle right there, and one of them is going to be sort of spiraled, so they're not going to be like in the same plane as each other. So this one, we have this carbon sort of sticking out of the screen. These will be sort of sticking into the screen, where this ring right here is sort of flat with the screen. And so these fused cyclic alkanes here are going to be the most common ones we see. These bridge ones are a little bit less common, and then these spirocyclic are the least common. Then so we have the naming convention here. So we see like this bicyclo, then 4,4,0 decane. And so the numbers in the square brackets here are just the number of carbons in each ring on it. And so we see on this one here we have 1, 2, 3, 4, and then we see here we have 1, 2, 3, 4, and so that is what the 4, 4 is. And then the 0 comes from the fact that there are no other carbons between the two bridgehead carbons, and so that's what that 0 is. So we have 4 from this ring, we have 4 from this ring, then 0 because there are 0 carbons between it. Where we see over here, we now have the 2, 2, 1 because we have 1, 2 carbons there, 1, 2 carbons there, then we have 1 carbon there, so it's 2, 2, 1, and so we call that bicyclo 2, 2, 1 heptane. And so we always just use this bicyclo here, and then it's the numbers in these square brackets that will sort of let us know whether it's a fused bicyclic, because that will have this 0 here, or if it's the bridged bicyclic, because that will have a non-zero right there for that third number right there. But then what we see is we call this decane, and that's because we have, if we ignore the numbers I have there, so I'll put this in different color. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons on there. Where this one is called heptane because we have 1, 2, 3, 4, 5, 6, 7 carbons on it. So the heptane and the decane from here come from sort of the total number of carbons between both rings there. So we see with the spiro here that that we now just have 2 numbers here in the square brackets, and that's because there is just a single carbon shared between them, and so there isn't going to be a third number because there's never going to be any other carbons in the middle there. And so this this ring has 4 non-shared carbons this ring has 4 non-shared carbons, so it's spiro 4,4 nonane, where uh, so between all of the carbons on here, there's going to be 9 of them, and so uh, it is the nonane backbone there. And so we can also get these conformations, like with this fused bicyclic, which we see here in parentheses, is sort of just shorthand called decalin or decalin there. So we can have the trans decalin and cis decalin, where the carbons here have the hydrogen going into the screen and coming out of the screen, or we can have the cis where they are in the same direction here. And that will actually change the structure of the ring in 3 dimensions, where we see in this one, both of these are in this chair conformation, but they are sort of, continuous with each other. Where in this one, again, they are both in chair conformation, but this one is sort of, sticking this way, where this one is sort of sticking downward like that, because this hydrogen and this hydrogen are sort of coming off of this in the same direction, where in this one, the hydrogen and this hydrogen are coming off of it in different directions. And so, yeah, that is what I wanted to say about the cyclic alkanes here. So I think, I mean, other than just sort of the general properties of it, probably the biggest thing to take away is just the sort of the chair and boat conformations is probably the thing that we will sort of be using the most going forward in this organic chemistry course. And so just knowing that the chair conformation is the most stable, and that the larger substituents always want to be equatorial, because that's going to be important for the conformation that these things take, and then sort of the reactions that these rings will be allowed to engage in, because when we start having these substituents on here, the substituents are going to have sort of steric hindrance of approaching other molecules. So we have some other molecule here that say wants to react with this ring. If this substituent is sticking out this way, it's going to sort of hinder anything from coming in from this direction. And so that's going to dictate like the way that other molecules, when trying to react with it, approach these rings. And so that's why this is important going forward. So it's not just like kind of a curiosity that these substituents want to be equatorial, and that the larger substituents are going to be equatorial over smaller substituents, because it's going to be important going forward as far as when we get to actual like reactions and things like that. So that's kind of the reason that we go through this, not just as kind of a, isn't that interesting that, these things want to exist in these certain conformations, which, I mean, science is about, just gee whiz kind of curiosity things, but it is also important in, like whether it can be helpful for us in predicting reactions and in trying to control the way reactions go. But anyway, I'm kind of rambling on here. I hope you found this video interesting and helpful, and I will see you in the next one.